Hello everyone, in this video we'll be discussing functions. And to get started, I want to say a function is a rule that assigns each element of a set, which is the domain of the function, to exactly one element of another set called the codomain. So the notation we'll be using here is that f is describing our function, so this is our rule, that takes a number or element from our domain, x, and assigns it to exactly one number of our codomain. So this is known as well-defined. Well-defined just means that it actually is a function. So this exactly one idea is very, very, very important. So if you have an element that goes to two separate elements, that's not a function. So very often we'll use these diagrams, like for example, 3 is assigned to 5, or 2 is assigned to -7 or something like that. But what you cannot, so these are okay, these are fine. But what you cannot have, a kind of non-example, is that the number 1 will go to two elements, 0 and 5. That is not okay. You can't assign two numbers from one number. Each element can go to only exactly one element of the other, so not to more than one. Okay, okay, that's I think all I want to say. I mean, you could have it, well, it can't even go to anything actually. It has to go to something. Otherwise, it won't be in the domain. So I guess maybe a kind of a little bit of a tangent example, but nonetheless an example, we write it over here, I guess, is the function f of x equals 1 over x. You may ask, well, okay, f of 2 goes to 1 over 2. So a diagram way of saying that is 2 goes to 1 over 2. But a big question is, what does 0 go to? Well, 0 would go to 1 over 0, which is not a number, right? So what that means is that 0 is not in the domain. Not in domain of f. If it was, then it would be assigned to something. So you can't even have elements that are not assigned to anything. If that was the case, it wouldn't be in the domain of that function. A little deep, I know, but that is something you can think about a little more if you want to. Two-line notation is using this kind of matrix notation, where the top row represents all of your things, all of your elements of your set, I would guess, or I guess of your domain, elements of your domain. And then here would be all elements of your codomain, and then what each of them map to. So you kind of think of these little arrows that map x's to y's and so on. So everything here is an element of x, and everything here is an element of y. So for example, here we have these elements of our domain that are mapped to these elements of our codomain. So I can say f of 1 is 2, f of 2 is 1, f of 3 is 3, and f of 4 is 1. And that is, again, because 1 maps to 2, see here, so that means f of 1 is 2, 2 maps to 1, so f of 2 is 1, 3 maps to 3, so f of 3 is 3, and 4 maps to 1, so f of 4 is 1. Okay. Now what this actually kind of describes is a pretty good example of the fact that our domain and codomain may not necessarily have the same size. And notice there are two things that get mapped to the same one number. That happens here with 1, which I'll show in blue, I guess. So for example, the numbers 2 and 4 both get mapped to the number 1, and that is perfectly fine. That it's possible for a function to have that phenomenon where you have more than one element from the domain going to the same single element in the codomain. That can happen. But the opposite cannot. You cannot have one element from your domain go to two elements in your codomain. That doesn't make sense. That would not be a well-defined function. Okay? Okay. So I think that's all I want to say here. And now let's, well, we're going to talk about a little bit more. And in fact, I'll kind of emphasize a little bit of what this phenomenon is called, and it has to do with this idea of injectivity, which we'll discuss right now. Okay, so now here we are discussing quite a bit, but I want to get into what are called injections and surjections. So first we need this idea of image. Okay, so if f of x equals y, then this means y is an output of our function f, where x is the input. So for an input, x, something from the domain, You plug that into f, and you get a corresponding output. And remember, there's no ambiguity because of well-definedness. So when you plug in something into f, you get exactly one thing. You don't get two outputs for a given input. You get exactly one output for a given input. Again, because of well-definedness. Okay. So here we say y is the image of x under f. So y is the image of x under f. So it's what, I guess, x is assigned to, basically. X is assigned to y. The range is a subset of the codomain whose elements are all images of the domain elements. So, I mean, it's a little hard to say in words beyond what I just said. I think this sums it up exactly. It's a little abstract, so let me try to explain a little bit. So remember that what we usually see is we write f as a function that goes from x to y, where x is the domain and y is the codomain, right? Right. Now, just because y is the codomain doesn't mean that everything gets mapped to from y. So for example, let's say x is the set of numbers, well, let's use letters, a, b, c, d, and e. And x, that's x, and y is the set of, let's say, a, b, c only, okay? Or actually, let's go to d, but not to e. I guess we could, it doesn't really matter. But let's say a goes to a, b also goes to a, c goes to b, d goes to d, and e goes to d. Notice, the things that are in the range are not necessarily the entire codomain. So the range is a and d only. Okay? So A are A, B, and D only. So A, B, and D are images. They come from x's when you consider plugging them into f. So this number c here, this element c, is not in the image of f. There's no number or no element of x that when you consider plugging it into f, you get c as an output. According to this diagram, c is not in the image. So c is not in the range. So notice I say the range is a subset because y is the codomain. So y is the set a, b, c, d, and so on. But the range of f, we call it range of f like this, is not y itself. It's a, b, and d. But notice this is clearly a subset of y. It's a proper subset of y. So hopefully range now makes sense. Okay. Now, a function is injective, or one-to-one, if this statement is true, this implication is true. F of x1 equals f of x2 implies x1 is equal to x2. This basically says that something like this, where two inputs go to one output, does not happen. If this were to happen, then f of a equals a, f of b also equals a, but b is not equal to a. So for our example here, we have f of a equals a, and f of b also equals a. Those are images under f of b and a. Okay. But notice, a is equal to a, so f of a is equal to f of b, right? That's true. But that does not necessarily imply that a is equal to b. A and b are different elements here. They're not the same one element. So this is not true. So this is not injective. So if you have something like this, where two elements of x go to one single element, the same element of y, that right away is not injective. So it's easier to tell when something is not injective versus when it actually is injective. You have to kind of see if this statement is true, which is harder to show, I think. Okay. A function is surjective or one-to-one if the range is equal to the codomain. So everything in the codomain got hit from something. You could still have this happening, right? It's possible that, in fact, it would have to be the case here because you have more things in x than you have in y. So you'd have to have at least two things go to one thing. So it's possible for a function to be injective, or not injective, I should say, but still be surjective. And again, surjective just means everything in your codomain got hit from something in your domain. Okay, so here I have two examples. This example, I'm not describing what our domain and codomain are. I'm just saying f of x is equal to x squared. Now, usually what we kind of assume when it's not emphasized, like in an example like this, is that f goes from the real numbers to the real numbers. And if you were to graph f of x equals x squared, that parabola you get is assuming x, your domain, is the set of all real numbers, and y, your codomain, is a set of all real numbers as well. So you end up with this kind of Cartesian plane here. And this is the parabola x squared. Now notice there's a lot of numbers that correspond to the same output. So for example, 1 and negative 1, when squared, both give you 1. So this is not good because we have two elements of our domain that are assigned to one single number in our codomain. So I'm actually going to show that more specifically here. And I'll just pick, again, 1 as an example. So I'll say f of 1 is equal to 1, which is also equal to f of negative 1. But clearly, 1 is not equal to negative 1. So this means f is not injective. I'll just box this. I didn't specify what this example was asking, but let's say it was asking, is the function injective or non-injective? And it's not injective. Surjective it actually is because, okay, so surjective it's not surjective. Why it's not surjective is because if you square a number, as we saw with the parabola, the set of all y values that are on the parabola are actually on the positive y-axis, not the lower y-axis, or not the negative y-axis. So not all of R gets hit by this. In fact, f of x equals x squared will only give you outputs that are positive numbers. Squaring any real number gives you only a positive real number, not a negative one. So with that being said, this function is not surjective in this sense. If we were to kind of shrink this so that, or restrict the codomain so that it goes from positive real numbers only, from 0 to infinity, for example, then it would be surjective. So it depends where your codomain is, of course. Okay? But here it's also not surjective. I'm not going to write it down actually, but something to think about. Here, let's take a look. So is this injective and is this surjective? So what I'll do is I'll just do this. Instead of writing it out, I'll write injective over here. We'll put a check mark if it's true and a cross if it's not. And surjective over here, we'll put a check mark if it's true and a cross if it's not true. Okay, so let's see. Are there any two numbers that map to the same one number? Of course there are. 1 goes to 1, 3 also goes to 1, and 5 also goes to 1. So you have 3 things going to the single number 1. So yeah, this is not injective. No. What about surjective? Well, our codomain is 1, 2, 3, but our image only contains 1s and 2s. So our range of f is just the set of 1 and 2, which is not the entire codomain. See that? 3 is not there. So this is also not surjective. If one of these was a 3, and you had 1, 3, and 2, then this would be surjective, but still not injective. Okay. So, I mean, this is basically, there are a few more ideas to discuss in this section, which we'll see right now. But after that, the video will actually end. So that'll be it. So there's a few more things to discuss, which we'll see right now. All right, so here I have the last few ideas. A bijection is a function that is both injective and surjective. In other words, every element in the codomain is the image of exactly one element from the domain. Now, bijections are actually pretty important because it basically implies that you have an inverse function. There's a one-to-one relationship. In fact, injective is enough to say that there's an inverse function, but a bijection is actually more so such that anything in the codomain came from exactly one thing. So it's something to think about. We won't really be taking a look at it too much in this section anyways. But the next two I want to see an example of. So first I have the inverse image of a subset B of the codomain of the function, which is a set F inverse of B, which is the set of all elements in the domain such that they get mapped to an element in B, which again is a subset of the codomain. Okay. And then the inverse image of an element, not of a subset, but of an element, Y, of the codomain is the set F inverse of Y, so it's a set, not a number, okay? Not a single element, but a set itself, of all x values in the domain X, such that f of x is equal to y. Now this makes sense because it may not necessarily be the case that f is injective. So there may be a number of things that actually go to y, they get mapped to y. So for example, x squared, if f of x is equal to x squared, f of 2 and f of negative 2 are 4. So the inverse of 4 is the set containing 2 and negative 2. Okay. Why? Because negative 2 and 2, when squared, both give you 4. So it's something to think about there. Now, in this example, I want you to find inverse image of an element and of a set. So we'll do it right now. But here we're defining f to be the function f of x such that f of x is the absolute value of x. So you take the absolute value of your input, and that's your output. So what is the inverse image of 10? So what numbers can you plug into f, into the absolute value that give you 10? Of course, 10 and negative 10. So f inverse of 10 is the set of numbers negative 10 and 10. Why? Because when you take these numbers and plug them into absolute value, you get the image 10. This one's going to be a little harder to see, but the inverse image of the set of all real numbers between 1 and 0, including 0 and 1. So this is I said 1 and 0, I meant 0 to 1. But this is the closed interval, right? So this is, again, the set of all real numbers that go from 0 to 1, including 0 or 1. So we want to find real numbers that when you take the absolute value, you get numbers in between 0 and 1. A little harder to think about, but if you consider numbers on the real number line, let's say 0's in the middle, and we have 1, 2, and 3. Let's go up to 2, I think is okay, and then negatives also. So negative 1, negative 2. So notice if you take the absolute value of 2, it's equal to 2 itself, which is not in this interval. So that's going to be excluded from our set here. It's not in the inverse image. In fact, anything that is bigger than 1 is not in the image. If you take the, or in the inverse image, I guess. If you take the absolute value of anything bigger than 1, you get something that's also bigger than 1. And similarly, if you take the absolute value of anything that's less than negative 1, then you get something that's also bigger than 1. Okay, but anything that's in between negative 1 and 1, when you take their absolute values, you actually get things that are in between 1 and 0. Notice 0 goes to 0, 1/2 will go to 1/2, which is in between 0 and 1. Negative 1/2 will also go to 1/2. So in fact, the inverse image of 0 to 1 for this function in the absolute value of x is exactly the closed interval negative 1 to 1. So that's a little harder to kind of envision, but that's the kind of main idea there. You take a look at what you can plug in to get this, and it's all things that are in this set. Okay, so that's all I wanted to say for this discussion on functions. I really hope you all enjoyed, and I'll see you in the next video. Thank you for watching. See you then.